Hello, I'm Pradeep NB, Assistant Professor, Department of Mechanical Engineering, Jawaharlal Nehru National College of Engineering, Shimoga, Karnataka State, from India. Dear friends, today I welcome all of you for my presentation on synthesis and characterization of bulk nanostructured titanium alloy. My presentation outline goes like this. It starts with the introduction, literature survey, objectives of the work, experimental work, results and discussion, and finally conclusion. Let us start with the introduction part. At present, as all of us know, the titanium-based alloys are of great interest in developing the metallic materials since titanium alloys have gained popularity as orthopedic implants in recent years due to their favorable mechanical properties, which includes low specific density, high specific strength, high strength to weight ratio, reasonable wear and corrosion resistance, and excellent biocompatibility. So that's why the titanium based alloys are finding its applications in most of the biomedical implants. As all of us know, the next alloys, next to the steel and cobalt based alloys, the titanium based alloys is finding its way as the new alloy for the implanting in biomedical applications. And along with this titanium addition, in addition to this titanium, magnesium is used as the alloying element because of its low modulus, high biocompatibility, low density, and good biodegradability. Alloying magnesium with the titanium will favor the lot of properties which are biocompatible to human body. Along with that, since the strontium and magnesium is orally administered to the human body. These two elements will favor the most of the properties that are good for the biomedical applications. And strontium, because of its good biocompatibility, bone mineral density, and it increases the bone strength, and it is used in the treatment of osteoporosis. Strontium as an additional element to this base element, that is titanium, will favor most of the applications, will favor most of the problems for biomedical application. When it comes to the literature survey, an extensive literature survey so far developed titanium alloys. An extensive literature survey is carried out among the literature survey. We found that titanium with magnesium as well as the strontium element will favor the alloy, titanium alloy that is good biocompatible as an implant material, and also good biocompatible for biomedical application. Say the addition of these strontium and the magnesium alloy to the titanium alloy will not only increases biocompatibility, it also helps in the corrosion resistance and the degradation, and it slows down the rate of degradation. Therefore, the possible application of the ternary titanium, magnesium, strontium alloy with high strength and low density as biomaterials is attractive. Hence, this investigation is carried out in developing the TIMGS or ternary alloy with high energetic ball milling process for biomedical application. And the objectives of the work goes like this. The first is to synthesize the nanostructured titanium, magnesium, strontium alloy by mechanical alloying technique, and consolidating the alloyed powder by cold isostatic compaction to study the effects of structural parameters, phases identification, and quantification during mechanical alloying using XRD technique, also to study the alloy powder. um, the compositional and surface morphology scanning electron microscope with energy dispersive spectroscopy is examined during mechanical alloying. Also, in order to find out the crystal structure, that is the structural parameter of the alloyed powder as well as the compact sample, it is examined using the transmission electron microscopy, that is TEM analysis is carried out to know the crystal structure of the alloyed powder as well as the compact sample. Also, to investigate the thermal behavior of the alloyed powder along with the compact sample, a differential scanning calorimeter was used for the investigation, for the thermal investigation of the alloyed powder as well as the compact sample. Experimental work. See, the mechanical alloying is one of the most important technique. I think I think we know the effective way to improve the atomic interdiffusion through continuous cycle of flattening, cold bending, and fracturing of powder particles is possible only by the route of mechanical alloying. Hence, the elemental powders of titanium magnesium in the atomic ratio uh, t- t- 70 is to 10 is to 20 is ball milled in an inert gas atmosphere at 200 rpm using the tungsten carbide as a milling media in the weight ball to powder weight ratio 10 is to 1. It is mechanically alloyed using the high energetic ball milling process, and later the alloyed powder sample was subjected to the structural investigation using the X-ray diffractometer. Using the X-ray diffractometer technique. Also, the thermal behavior of the alloyed powder and the compact sample was determined at room temperature using the DSC. Topography and the surface morphology were also evaluated by the SAM and the TAM SADP pattern. After that, after alloying it for 30 hours, then the alloyed powder particles was consolidated by the cold isostatic pressure, and then the similar characterization is performed in order to know the structural parameters, phase evolution of the compact sample. This is a mechanical alloying technique. This is a high energetic planetary ball milling equipment which was used for the synthesis of the nanostructured TIMGSR powder using the mechanical alloying technique. These are the ball milling specifications. The table shows the ball milling specifications. Ball to powder weight ratio 10 is to 1 milling media. Tolling speed, it was around 200 rpm. Ball material and oil material are the same tungsten carbide. Container volume capacity 250 ml. Ball diameter each ball diameter it's around 10 millimeter, and weight of each ball is around 7.5 grams. The number of balls used for the milling process was 99. The total weight of balls it was 742.5 grams. Total milling time carried out, where total milling carried out it is for a duration of 30 hours. Next. This consolidation of powder was performed using this hydraulic press at a pressure of 500 megapascal. The powder was compacted, and the cylindrical compact dimension was it is of 10 mm in diameter and 10 mm in height. After this cold compaction, it is dried at room temperature. Then the green pellet was taken out from the die, and then the compact sample is subjected to microwave sintering at a temperature of 300 degrees Celsius in a microwave for a furnace for 1 hour duration. And later, the compact sample was characterized to know its structure and properties. This picture shows the compact bulk compact sample which was synthesized from the 30 hours of ball millet powder. Nano indentation test was carried out in order to know the mechanical properties of the, in order to study the mechanical properties of the compact sample. Nano indentation test was carried out, that particularly the hardness as well as the Young's modulus. In order to know the Young's modulus of the sample, nano indentation test was carried out. When it comes to the results and discussion, this XRD characterization of the milled powder as a function of milling time. This graph shows XRD profiles of ball mill powder at different hours of time, that is 5 hour, 10 hour, for 15 hour, 20 hour, 25 hour, and 30 hour. At each interval of 5 hours, the small quantity of powder is taken out from the jar for the characterization purpose, and the characterization, XRD characterization shows for every 5 hour the peak broadening that takes place at the, we can observe that at 0 hour of at the initial ball milling time, that is at 0 hour, it can be observed that the peaks are very narrow, and the powder, that means it presents the crystallinity in the powder. As the milling progresses to 5 or 10 hour, 15 to 20, 25, and 30, the peaks gets broadening, and the we can observe that the shift in the peak, it is due to the alloying the process between each elements. These are the Bragg angle and structural parameters of the XOD peaks at different ball milling duration. We can observe that as at the end of 30 hours of ball milling process, binary phases are formed. That means the binary phases of strontium, titanium, magnesium, strontium, magnesium, titanium oxide, along with the elemental phases, titanium, magnesium, strontium, was observed at the end of 30 hours of ball milling process. It represents that the alloying has taken place between the titanium, magnesium, magnesium, strontium, and strontium, titanium. And at the end of the 30 hours of ball milling process, due to the ball to ball and ball to wall collisions, the powder size reduces to 30 nanometer as the milling progresses up to 30 hours of duration. Earlier it was in the microns. Micron size of the powder particles was in microns. Later it was reduced to the 30 nanometer because of the ball milling process, and also due to the mechanical alloying, the binary phases formed at the end of 30 hours of ball milling duration. And this graph shows the variation of the crystallite size versus milling time. As the milling progresses to 30 hour of ball milling duration, the crystallite size goes on has reduced, and the blue color curve, it shows the lattice strain increases as the crystallite size reduces due to the ball milling duration, due to the increase in the ball milling duration. And this SEM analysis of the ball milled and unmilled and ball milled powder sample, it represents the unmilled powder sample where the powders are seen, and as the milling progresses up to 10, 20, and 30 hour, the some micrographs, it shows the flake structure of the powder particles and the agglomeration of the powder particles, and the cylindrical structure and spherical shape of the fine powder particles due to the cycle of fracturing, cold welding, and flattening of the powder particles. And the results were confirmed with the help of some with the DAX, as we can observe the composition of each element was present in the ball milled powder sample. When it comes to the time analysis, these are the diffraction rings where we can observe in the ball milled powder at 30 hours of duration. Minute dots are present on the rings, on the diffraction rings, which represents the elements that are present in the ball mill powder. And in this diffraction, this here in this, the diffraction rings are too diffused, and it suggests that the partial amorphous structure we are observing, and also the crystallite size reduction to the nano scale regime. And these are the indexed SADP patterns of the ball mill powder for 30-hour duration. And these are the elements HKL. Okay, after indexing the each diffraction pattern, it is found that the similar elements were present, and these results were confirmed with the XRD results, as the same elements are present in the powder ball mill powder sample. This 10 micrograms of mechanically alloyed powders of 30-hour ball milling duration. You can see the small minute particles that are present, which indicates the nano size of particles are present in the ball mill powder sample. When it comes to the DSA analysis of ball mill powder, uh, it can be observed that the heat flow, it is around at a temperature of the 10 one around 110 to 120 degrees Celsius, where the phase transition has taken place from phase transition from the crystalline to amorphous structure has taken place at the temperature range of 100 to 150 degrees Celsius, and that which suggests that the formation of new phases at the cost of ball milling process. This shows the curve of the heat flow endothermic heat reaction that has taken place during the ball milling process, and the phase transformation has taken place in the during the ball milling process. And the nano indentation result, when it comes to the nano indentation test, this micrograph represents the Berkovich indenter, the mark that is present on the sample where the indentation test was carried out at location 1, location 2, location 3, location 4, and location 5. This was a result. The Young's modulus value modulus versus the displacement into the surface of the specimen, where we got the and this graph represents a hardness versus displacement curve of the specimen, and this graph represents the load on sample versus displacement. And here we get the value at five different locations. The average modulus got the average modulus of 24.814 gigapascal was found, and hardness of 0.84 gigapascal was found. The mean value from the five locations, as well as the load at maximum, it was the 30 millinewton. We found that the low Young's modulus, which is favorable for the biomedical implants, since low modulus titanium alloys will benefit as an implant material for biomedical applications. Since if it is a high modulus, then it will end up with the stress shielding effect. So low modulus titanium alloys are preferred for the implant materials in biomedical applications. Hence, in our present investigation, we got the low modulus value of 24.5 gigapascal than the other when we compare that with the other titanium based alloys, and this alloy is found to be most favor for the biomedical applications as an implant material. This is a XRD analysis of the consolidated compact sample, where it shows the similar fuses which are present in the ball milled powder for 30 hours duration. That is magnesium strontium along with magnesium strontium binary phase. We have the elemental phases of titanium, magnesium, and strontium. This table represents the structural parameters and phases of the consolidated sample, and we have the HKL factors along with the phase percentages. This microstructural analysis of the compacted sample by SEM with ADS, it represents the elemental composition that are similar with the elements that were present in the ball milled sample. And after that, the time analysis of the compact sample, it shows the diffraction rings with a small star-like spots on each diffraction rings, which represents the phases that are present in the ball milled powder sample. And these are the nano grains that are seen that we can observe in the compact sample where we retained the nanostructure in the upon when we sinter any sample. Normally the particles, the grain growth occurs, but since we sintered the sample at low temperature, we were able to retain the nanostructure even after the sintering process. That is indicated by the nano grains in the TEM images of the in the TEM characterization of the analysis of the compact sample. These are the indexed TEM indexed SADP patterns of the compact consolidated sample, where each diffraction rings shows the crystallite stars, which represents the elements that are present, that are identical with the elements of the XRD characterization. Conclusions. From the XRD study, we come to conclude that the ball milling process, at the early stage of the ball milling process, which indicates the narrow peaks that presents the elemental powders and the intermetallic compound, that is MgS or MgTiO, that is formed at the end of 30 hours of ball milling duration. It is because of the ballistic diffusion of magnesium atoms diffuses into the crystal structure of titanium, and shifting of the diffraction peaks to higher Bragg angles. It suggests that it is a phenomenon related to the formation of new phases. However, distinctive phases have emerged during the ball milling phenomenon, which suggests that it is all because of the severe plastic deformation that occurs during the ball milling process, that helps in the distinct phases to emerge as a result of the mechanical alloying process. And also the morphology, when it comes to the SAM and TAM study, the morphology of amylose powder, it shows more irregular in shape without any deformation, and the changes in the form of the powder, it is due to the deformation that can be seen by the flattening and typical popcorn structure from the increase in the ball milling duration. And the spots of the black dark spots in the 10 SADP image indicates that the nanocrystalline grains, and the smoky image always suggests that the amorphization has taken place from the crystalline to amorphous structure, as the transformation has taken place during the ball milling process. And the increased crystallite size rate represents the significance of the peak narrowing in the XOD profile of the consolidated compact samples. It's always it's an usual, as we all know that during sintering the grain growth will take place, which suggests that is suggested by the peak narrowing of the XOD investigation of the compact sample. And the measured values of the nano indentation test shows the low Young's modulus of around 48 gigapascal and hardness around 3 gigapascal, which is nearer to human cortical bone when compared to that so far developed the beta titanium alloys. So in our present investigation, the so developed titanium magnesium strontium alloy, which possesses low Young's modulus, is preferred, and it is favorable favorable for the biomedical implant application. Thank you. I thank all of you. I thank all the audience for patience listening, and I thank the organizing team of the Science Father Award, that is for giving for selecting me and nominating me for Best Researcher Award for the year 2022. I thank once again for the team of Composite Materials Science Father.